use a triple integral to find the volume of the solid enclosed by the paraboloids y equals x squared plus z squared and y equals 8 minus x squared minus z squared. I'd like for you to set this up, but I want to give you a little bit of guidance. Because we can see that y is bounded by two paraboloids, I'd like for you to draw the region in space, of course, in R3. And I'd like for you to set up an integral of the form a double integral over d of an integral of dy dA. Because we're using a triple integral to find the volume, our integrand is 1, so there's that. But what I want you to do is I want you to figure out what are the limits on y, and then we'll come back and talk about d. Go ahead and pause it and set this up as much as you can. Here's what I've got so far. We have the blue paraboloid, which is its center on the y-axis, and it opens in the positive y direction. And then we have a green paraboloid, which has a vertex at 8 units out on the y-axis, centered on the y-axis, opens in the negative y direction. And so here they are, they meet together, and where they meet is a circle because we have, it's a circular paraboloid, right? Setting the expressions for the paraboloids equal to each other, we have x squared plus z squared is equal to 8 minus x squared minus z squared. We're going to see that that's a circle of radius 2, right? It simplifies to x squared plus z squared equals 4. That's the trace in the xz plane. That is our region D. As far as y is concerned, y goes from one paraboloid to the other paraboloid, and so we see the inequality y goes from x squared plus z squared to 8 minus x squared minus z squared. That gives us our limits on y. So we have the double integral over d of the integral from x squared plus z squared to 8 minus x squared minus z squared of dy times dA. And I'm doing this way for a particular reason. If we look at our region D in the xz plane, it's a circle of radius 2. Folks, if my region D is a circle, I'm probably going to go polar coordinates. And in this case, because we're in the xz plane, I'm going to let x equal r cosine of theta, and then z equal r times the sine of theta. And you'll say, what polar coordinates are x and y? Yeah, but look, it's a circle in the xz plane, and as far as the polar coordinates are concerned, they don't care if it's x and z. With this now in mind, I'd like for you to convert the integral that we have into one in polar coordinates and then compute it. Come back when you're done. For our polar coordinates, because we are looking at a circle of radius 2, we know theta is going to go from 0 to 2 pi. R is going to go from 0 to 2. Our integrand is r dy dr d theta. Don't forget dA in polar coordinates is r dr d theta. The limits on y become, well, x squared plus z squared becomes r squared, and then 8 minus x squared minus z squared becomes 8 minus r squared. We have an integrand that's simply r, and so I've split this up into two integrals, and I'll explain. One of them is the integral from 0 to 2 pi d theta. That's multiplied by the integral from 0 to 2 of r, and then I went ahead and evaluated, I integrated with respect to y, and then put in the upper limit of 8 minus r squared minus the lower limit of r squared. So what I have is the integral from 0 to 2 pi d theta times the integral from 0 to 2 of r from the r dr d theta times the quantity of 8 minus r squared minus r squared from the upper and lower limits of y. All of that is still times dr. I made a little note to myself here inside the parentheses. 8 minus r squared becomes 8 minus 2r squared, and then distributing the r is going to give me an integrand of 8r minus 2r cubed. The integral from 0 to 2 pi d theta is simply 2 theta, and then integrating 8r minus 2r cubed from 0 to 2 is going to give us 4r squared minus 1/2 r to the 4th. That'll be evaluated from 0 to 2. Our final result is 16 pi.